Good morning, committee members, session chairs, and attendees at APSCon 2024. I am Anisha Palkar and Meera Radhakrishnan are pleased to honor our paper titled Designing Tunable MEMS-based Ionizing Radiation Dosimeter for Healthcare Applications. Both of us are second-year MTech Medical Informatics students originally from MIT Manipal and working as PG interns at Innvolution Healthcare Private Limited, Bangalore. So in an era where technological advancements are paramount, our research is led by us in collaboration with Samhita, Varsha, and Dr. Arindam Kushagra, which addresses a critical need in healthcare. So our presentation embarks a journey to revolutionize the ionizing radiation dosimetry with leveraging the MEMS technology. This innovative approach has helped to give a tunable, precise, and accurate measurement for monitoring the ionizing radiation dose. As we delve into our presentation, I would like to invite all of you to join with us in envisioning the future of ionizing radiation dosimetry. Without further ado, let's go to the presentation. So going to the overview of our presentation, we would explore the diagnostic approach for coronary artery disease, which would emphasize the cath lab procedures which are carried out, that is angioplasty, angiography, the interventions, which comes with the detrimental and potential harmful effects of X-ray radiation caused to the patients as well as to the doctors. Hence, we shift to the dynamic mode X-ray dosimetry, utilizing the micro cantilever and MEMS technology. As we navigate to the presentation, we would explore the radiation monitoring, advanced procedure like with dosimeters, MEMS, and micro cantilevers. And this mechanism can be enhanced. The sensitivity can be enhanced by integrating NIPAM, that is N-isopropyl acrylamide polymer. In conclusion, we will just summarize the key elements and how this can signify the future of radiation dosimetry. As we go to the diagnostic, going to the coronary artery disease, the condition is marked by a buildup of plaques, that is the which is in the coronary arteries, that can be a calcium or fats, which restricts the blood flow going to the heart and causes chest pain, that is angina, or heart attacks. Hence, this coronary artery disease can be diagnosed with the help of angiography, which plays a vital role in imaging the high precision, which utilizes high precision imaging and advanced technology for detailed visualization of the blood vessels and to find out exactly where this disease has been caused. Hence, when we go through the procedures, this angiographic procedure is carried out in a catheterization laboratory where real-time interventions are carried out. It ensures optimal accuracy and effectiveness in cardiac procedures. So this is a catheterization lab system where the interventions, it can be immediate or targeted interventions are carried out. When this diagnosis interventions are carried out, it comes with parallelly harmful effects which are caused to the patients and to the doctors. In case of patients, it can be due to the burns and skin problems. Because of the prolonged exposure, it can also cause risk of cancer. And for the doctors, because of the scatter radiation, because they're in close vicinity of the patients where the X-ray radiation is being exposed, it contributes to the health issues like cataracts or arthritis. Hence, this emphasizes the need for optimal X-ray radiation dosimetry in medical imaging. So going to our dynamic model, where what we have proposed through this paper, where we are integrating the MEMS technology, that is micro cantilevers. So it utilizes MEMS platform with micro cantilevers for innovative monitoring. It helps to give a cost-effective design where the features of polymer, so NIPAM is coated on the MEMS technology, and this mechanism helps to give a precise dosage measurement, which helps in affordability and viability. Further, it is also an adjustable sensor response. So whatever the temperature changes takes place, it gets adapted to it and it tunes the temperature. It ensures in flexibility in any diverse conditions. Hence, it does not only meet but also surpasses the critical need of measuring the radiation exposure. This helps to minimize the health risk for the researchers, health professionals, patients who are who are being exposed this ionizing radiation, hence giving them safety and as well as safe environment to work in. So as we go ahead, in depth of our research work, I would like to introduce Meera, who would give the key elements and the findings of our research work.
Thank you, Anisha. Now I'll be explaining about the MEMS radiation dosimeter, MEMS microcantilevers. So starting with the radiation dosimeter, so it's a device which is crucial for assessing absorbed quantities, and plus it also gives a continual monitoring of cumulative radiation doses. It also provides health concerns, protective and proactive health concerns, and another measurement is DAP, which is dose area product. Now going forward with the MEMS, which is micro electromechanical system. So integrating it offers precise and accurate measurement because of its very small, small size. And the simplified form of MEMS, which is micro cantilever, it offers sensitivity and ionizing radiation through resonant frequency shifts. Now, when talking about the X-ray impact and resonant frequency prediction, so when X-ray is exposed on the microcantilever, silicon-based microcantilever, hydrogen diffusion occurs, and because of this impurity scattering, what happens is the concentration, the carrier concentration increases, and because of which the sensitivity increases, causing a decrease in the resonant frequency. Now, the hydrogen trapping rate is proportional to the surface to volume ratio of the microcantilever, and again it is equal to the hydrogen boron dissociation. Now because of this, the device stays in its equilibrium state. So now when all these hydrogens are trapped, the device moves out of its equilibrium condition, causing a decrease in the resistance monotonically. Now when the radiation is switched off, all the processes goes reverse. So this is the X-ray impact on microcantilever. Now moving forward with the proposed design. So NIPAM is coated on this silicon cantilever, and NIPAM is N-isopropyl acrylamide, and it is known for its water solubility and reverse thermoresponsive behavior. And so when radiation is exposed on NIPAM, what happens is the lower critical temperature or the cloud point of NIPAM increases from 32 degrees Celsius to 34 degrees Celsius. And this causes the NIPAM to behave as a hydrophilic, because of which the NIPAM swells. And because of swelling of NIPAM, cross-linking of the copolymers increases and it forms gelation. So this is the swelling behavior of NIPAM. Now, as the dose rate increases, the cross-linking density also increases and it limits the swelling ratio. As the temperature goes beyond the LCST, it behaves hydrophobic and the NIPAM shrinks. Now this shrinkage causes depolymerization of NIPAM. So this is the behavior of NIPAM with respect to temperature. So this is the NIPAM coated cantilever structure where X1, X2, XL are the dimensions of cantilever. And talking about the phase transition and surface stress dynamics. So as I mentioned, when NIPAM swells, it imposes a tensile stress on the cantilever, because of which a polymer absorption induced bending happens to the cantilever. And similarly, when NIPAM shrinks, compressive stress is imposed on the cantilever, because of which it induces a curling of the cantilever. So now talking about the relationship between surface stress and the resonant frequency. So this is the equation which shows the relationship, and EI is the flexural rigidity, mu is the mass per unit length of the cantilever, L is the length of microcantilever, and sigma, which is surface stress, is considered to be positive or greater than 0 when it is tensile and less than 0 when it is compressive. And function of X is the change in shape of cantilever dimension x1, x2, and beta, it remains positive for all the values of x1, x2, and L. So this is the graph, simulated graph. Yeah, sure. So this is the simulated graph which underlies our assumption. So the NIPAM's hydrophilic nature, it causes a positive surface stress and it results over increased resonant frequency and right shift. And the NIPAM, when shrinks, it causes a negative surface stress and it leads to a decreased resonant frequency and a left shift. So now I would like to conclude the presentation stating that this study has tailored MEMS platform for superior performance in monitoring X-ray exposure directly, which addresses the demand of our industry as well. And the incorporation of MEMS has given a dynamic approach towards optimizing dosimeter functionality. And our research not only contributes to the evolution of healthcare application, but to the industrial application as well. So these are some of the references we mentioned, and would like to extend our sincere gratitude to Innvolution Healthcare Private Limited and the team. So thank you.